Okay, so we are into this sixth session, and in the previous lectures, we have seen what is engineering meteorology, what are the different attributes of engineering meteorology. Then we went on to study about the mechanical measurements, manual measurements. Then we understood the facts and concepts about measuring things, their properties, what are the nooks and hooks that we should take care of. And from there we went on to study that how we transited from completely manual measurements towards digital measurements. And then we understood the concept of transducers, and in the concept of transducers we understood the concept of energy transformation. And in the last class we discussed about different kinds of energy transformations. And today we will begin with temperature measurements using these digital sensors. So the first topic that we will cover today is the temperature sensors or temperature measurement. So let's not call it sensors but keep it temperature measurements. Now we have seen previously that for any measurement the weight is important, and along with that weight the units are also important. So if I talk about temperature measurements, the conventional method that comes to your mind, the first thing that we know that does a temperature measurement is a thermometer. We have seen people using thermometer, medical practitioners using thermometer for people who have high temperatures, and it is a glass tube that has mercury filled inside and displaced on one of the body parts, and with the rise in the temperature on the bulb the mercury starts to rise. We all have seen that structure. So this is the typical design of a thermometer, where this is the bulb, this is the glass tube. Here on the body there are several markings for the temperature. And then there is mercury filled all over here. Now liquid mercury has its own properties, because of which it becomes very suitable for human body temperature measurements. Why? Because the range of human body temperature is typically from, say, 94 degree Fahrenheit to something near about 108 degree Fahrenheit. And within this range, we get by and large all the temperatures that exist in the human body. So these temperatures are easily accessible, and sensitivity is a very important factor while designing a sensor system or a measurement system. And how do we define the sensitivity? Is the reaction of measurand or measuring unit to changes in the quantity being measured. Now suppose we designed a system for zero point 0.1 degree Fahrenheit of increase or decrease in the body temperature. Now that is critical while observing the human body temperatures, because the range is from 94 to 108 degrees Fahrenheit. Now suppose if glass mercury, this liquid mercury was not capable of giving temperatures in the range of zero point 0.1 degree Fahrenheit, and suppose it gave temperature ranges between say 2.2 degrees Fahrenheit or 2.5 degrees Fahrenheit. In that case, we would have only read temperatures like 94, 96, 98, 100, and we would have missed the intermediate numbers here, 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 and so on and so forth. So our readings would always have been at a distance of 2 units, which itself is a very large variation while we are studying temperatures. For elderly patients, for younger patients, for everybody, if you can measure this at a distance of 2 units, you are missing out numbers. So this sensitivity of the material is very important, and with this sensitivity we make the choice of material for the transducer. Now we have seen in the previous class that transducers are defined as uh, elements that convert some form of energy into electrical form. But here, when I'm calling a temperature thermometer and it's mercury as a transducer, then it is not typically giving us electrical voltage, but what it is giving is, with the rise or decrease in temperature, the length of liquid filled in the tube rises or decreases. Length of filled liquid mercury. So this is the property of mercury, that with the rise in temperature, there is expansion of the material or mercury. Now this itself is a form of transduction. The word is transduction. The elements are called transducers and the phenomena is called transduction. So this transduction happens, and with rise in temperature, as soon as the temperature rises, what we get is the expansion. And this itself is a physical variation. If instead of this expansion we would have got a rise in voltage, it would have been a typical example of a transducer. So although this mercury thermometers are not transducers, but their behavior is almost similar. What they are doing is they are showing some physical variation with the rise in temperature. And hence we have been using these thermometers for quite some time in medical history. But there are also cases wherein the temperature range is 1000 degrees Fahrenheit or even more. Now, our mercury filled temperature glasses are not suitable for this range of temperature. And the temperatures that we deal with in some scientific situations may even drop down to say minus 250 degrees Fahrenheit or even lower. So this medical grade liquid mercury thermometer won't work. So we need to look for alternate measurements and also the techniques to design these systems. Now, before we go on to read other types of temperatures, sensors or transducers, let us first understand that the very important concepts of units of measurement. We have three units of measurements for measuring temperature. First is degree Celsius, the other is degrees Fahrenheit, and the third is Kelvin. Now, all these are scientific grade units, although there are more units called as Rankine, but these are the most prominently used scales. These two, in fact, are used in common day-to-day life affairs, but this is more for academic purposes. And they all have their own formulas of interchangeability that you all must be aware of. Like Kelvin is related with Celsius as is this right? Is this right formula? Or I'm missing out on something? Okay, you should check on to the, so the assignment for you is, the takeaway is that you should study and analyze the relations between three scales or three units of temperature scale. So it is important for you to analyze this also. Once you study, you should analyze that how did the scientists and the researchers came up with these formula and why were these three units actually needed. We could have done with a single unit or two units maybe, but for temperature we have 4 to 5 units. So why were they all needed and what are their historical perspectives? When were they designed and why each of them, yeah, most of them got discarded and we use prominently these three. We should study and analyze it. Now let us move on to the next topic in our today's discussion, and that are the thermistors. Now, thermistor word itself, so first of all, it is a temperature sensor or temperature transducer. Okay, before we move on, I have been using this word sensor and transducer interchangeably and invariably, but there are some differences between a sensor and a transducer. So the second assignment for you is, for today's class, is to study the differences between sensors and transducers. So when you'll do this, you will identify a very striking feature that both of these possess, which is very important for designing systems. And there is a very minute difference between these two. And how does these two very minute small difference creates two different classes of technology for us. So this is a takeaway assignment for you. Now let us come back to what thermistors are. So let us say for this class we will assume that sensors and transducers are the same things. So thermistor word is the combination of two words, thermal and resistor. So with this breakup, it is very sure that you can make it out that the material to be used in designing must have a resistance that corresponds to changes in temperature. Now what does this mean? A very basic and simple meaning of this is, say we have a resistance R and we know that this resistance R is made up of the properties of material, which we had seen in the previous lectures to be the resistivity and the dimensions of the material. For example, we know that resistance of a single element is rho L upon A, where rho is the resistivity of the material, L is the length, and A is the area. So if this is a material with a resistivity R, rho, length L, and cross-sectional area to be A, we can say that for this piece the resistance is R. Now, if at all I say that this length L is a function of temperature T. So what will happen? We will see this figure again here. Say we have a material with length L, area of cross section to be A, resistivity to be rho, and R for this material will be rho L upon A. Now I am saying this L is a function of time T, a temperature T. This means is if I apply a certain temperature onto this, so what I am doing is, let me put this tube of material on some flame. So if I put this length on flame and the temperature of this material starts to rise, so with this rise in temperature, because this length L is the function of temperature T, this length will start to change. So with delta T rise in temperature, suppose the temperature initially was T, so T plus minus delta T will lead out to L plus minus delta L, where T is the original room temperature, delta T is the variation. Similarly with L and delta L, L is the original length and delta L is the variation in the length because of the variation in the temperature delta T. So with the rise in temperature, with the increase in temperature or decrease in temperature, the length of the tube will start to increase and decrease. And similarly, I can say it for the area also. The area A is a function of temperature. Now this cross section will start to increase or decrease. And similarly, I can say for resistivity also. If the material permits, in that case, the resistivity rho can also be a function of temperature. Although it is constant for many materials, but with the rise and decrease in temperature, the resistivity might change. So if all the three are a function of temperature, we can say that this resistance is also a function of temperature T. Now, if we have concluded that this resistance R is a function of temperature T, then in this case we can also say that with the rise in temperature, the resistance of the material changes. Now I am using a very politically correct word of change here. I am not saying the temperature would the rise in temperature would increase the resistance or it would decrease the resistance. It can always be both ways, and that totally depends on the material. So here we have used the plus minus symbol both. And delta T is the variation. So the variation can be positive also and negative also. So similarly, the resistance change can, the temperature change can either increase the resistance or decrease the resistance. And now if we are in a state, if we are in a state that we can harness this change in the resistance, we can directly harness the change in temperature. So if you understand the cycle of events from here now, that with the rise in temperature, what follows is the rise in resistance R. And if we can calculate this change in resistance R, we can attribute it to the change of temperature. Now, how to harness this change in resistance? We know that V is equals to IR, a very simple Ohm's law. So say I have a battery with voltage V and I apply this length of material here, and I close my circuit here with a ground, and within this setup, if I subject my piece, I'm calling this length to be my piece, subject my piece to temperatures, what will happen? There will be a flow of current R depending on the resistance R of this resistance. There will be a flow of current I. So say I am calling this battery is fixed, V is fixed. So with this we found the relation V is equals to IR. Now say after applying the temperature T onto this piece, the resistance changed to RT, and because of that there is a fixed voltage here, the current would change to IT. So we would get a relation is equal to V is equals to IT RT. This resistance will change, increase or decrease depending this V I will also keep on increasing or decreasing in the similar fashion. So with this rise in resistance, we will see a change in the current I in the loop because this voltage V is fixed. Now if we measure this current I, we are actually measuring the change in temperature. So the line of command here was we found temperature, we had to find temperature changes. With the temperature changes there was change in resistance, and with the change in resistance the current I started to change in the loop, and by identifying this I we actually determined the temperature T. Now there is a very beautiful term here that is called as calibration, and which is the most critical section of designing the sensors. This is easy for us to understand and say that T, or rather R, is a function of T. But what is this function? What exactly is this function? And is this function a constant function or a varying function? In mathematics, it is very important for us to physically attribute the changes of the material with exact mathematical relations. So calibration is nothing but identifying appropriate mathematical formulations to correlate mutually varying subjects. Okay, so right now we had the convenience of saying that resistance is a function of temperature and I is a function of R. But to design a perfectly functional system, we would have to name this function f. We will have to identify the mathematical formula. And with the identification of mathematical formula, we will be able to completely tell that how much changes in the temperature would result in how much change in the current. So this how much, the quantification of the values is actually called as calibration. It is also important for you to know here that the calibration factor is purely dependent on the experiment design. We change the experiment, the calibration factor would change. Now what is this experiment design? We have used a specific material we have used a specific geometric arrangement and all other different variables. So either of this being changed, the calibration factor will change. It will not remain same for all the cases. So for thermistors, the material of our choice is semiconductor material. And with this semiconductor coming into picture, we have a negative temperature coefficient. So this implies that with the rise in temperature, the resistance of thermistor would decrease. So it is very important here that we chose semiconductor for designing thermistors. Why did we choose semiconductor? What semiconductor did we choose? Behind this is a set of experiments that continued for a long duration of time. And we found that using semiconductors, we get a larger range of operations and the lifespan of the system increases. But the thing that we observed was is the negative temperature coefficient. But we are indifferent to the fact that the rise in temperature is giving a decrease in resistance, because we just want to measure the difference that is arising because of the rise. So we are, rather than being dependent on T, we are more interested in delta T. or rather than being interested in R, we are more interested in delta R. So for the semiconductor thermistor, the kind of graph we get here is the negative coefficient graph, that the slope would be negative, would imply that for, let's say, this is my temperature scale and this is my resistance scale. So with the rise in temperature, the resistance would decrease. So for a very high value of temperature, we would have a very low value of resistance. And for a very low value of resistance, say here, or rather for a very low value of temperature, we would have a very high value of resistance here. So this is the kind of curve that we get here. So this will have a negative slope. So thermistor is the first class of temperature sensors or transducers. Next to fall in line is the RTD, that we call in short, or the resistance temperature detector. Now we have seen that the thermistor is a resistance whose values change because of the rise in the temperature. So in case of the thermistors, we have seen that it is directly connected to the rise and decrease in the temperature. And here in RTD, we have used the similar terms. We are saying resistance temperature detectors. So these are detectors that sense the rise and fall in temperature with the rise and fall in the resistance. So by definition, they are invariably the same thing. But how does this differ is upon, again, the choice of material. There, when we were discussing thermistors, we said that it is made of semiconductors. RTD, on the other hand, is purely conducting material. So the concept will by and large be the same, that we have a fixed voltage source on which we put our element. There is a current I, there is a voltage V, and V is equals to IR. So this R is an important factor, and this R is going to change because of the subjection of delta T temperature. So as soon as we supply delta T here, this resistance is going to change. So the experimental setup here is same, but the choice of material is different. We are here using purely conducting material like copper. And with pure metals or metallic conductors, the behavior has a positive coefficient. So what would happen here is, if this is the temperature scale and this is the resistance scale, for a very high range of temperature, the resistance would also be very high, and for a very low range of temperature, the resistance would also be very low. So the kind of curve that we get here is this, as compared to the previous one, which was this. So RTDs and thermistors are mechanism wise perpetually same thing, but they differ on the choice of material and hence their construction, and hence we get this curve. This is very important curve to understand the differences between the thermistors and the RTDs. The behavior would be different, the experimental setup would be the same. Now if we are clear with the concept of changes in the resistance due to temperature, we should understand one more important type of transducer here, that is a thermocouple, which is extensively used in the industrial applications in almost all kind of industries, and this is a very high grade design that can give you results in complex situations. So if I again try to break the name, I will identify two terms, thermal and couple. Now this always indicates two. So there are two thermal junctions, or maybe rather two thermal entities colliding at one junction. So if you can see here what I'm trying to draw, so this basically is a junction, and these are two different points, the hot point and the cold point. And what we are eventually trying to do here is, again, we have to measure the temperature of a point specific. Measure the temperature is our only aim. So we have a point whose temperature is known, and at the same time we have a point whose temperature is to be measured. So this we call as the hot point, and this that we know we call as the cold point. So what we do up next is, we bring the 2 points together in contact at a junction, and we have been knowing the concept of flow of energy from our early science studies, like the very old concept that we used to study about a towel, that if you put the towel inside a water bucket, due to the difference in the content of water on the both of the edges, the the water molecules will start to rise from the lower end towards the upper end. And this is the flow of energy, that there is a movement of particles from higher concentration of anything to the lower concentration of anything. Now this can be a higher pressure, this can be a higher temperature, this can be higher humidity. So there is always a movement of particles from point of higher concentration to the lower concentration. Now in this case also we have a point that has a higher temperature, and also we have a point that has a lower temperature, and that hot junction and cold junction we bring it together, and we say that this is a junction where we are bringing it out together. And because of this gradient of temperature, because of this gradient of temperature, a continuous flow will begin until saturation arises. So what is typically happening here is that when we are bringing in the hot and cold junctions together at one particular point, there will be a flow of particles that will start, and the temperature of the higher point will start to reduce and the lower point will start to increase, such that at one particular point they arrive at a same temperature, and that situation we call as saturation. Now when this happens, this flow of energy or flow of particles happen, there is a flow of current that is established. This is very important to understand here, that with this flow of particles, this flow of current is established, and this happens in accordance with the Seebeck effect. So what is Seebeck effect? Seebeck effect is nothing but the flow of current that is established between two different entities at different temperatures when brought in together. So Seebeck effect corresponds to I, the flow of current, when two different temperature points are approached towards each other. Okay, so what happens in the totality of this is, with the rise in temperature, the particles start to oscillate, and with the oscillations, the their mechanical motion starts, and with this mechanical motion they gain energy, so they hit something and they lose their energy there, and this flow, when it starts, it establishes a current because of the electrons moving inside the conductors. So this basically is called as the Seebeck effect, where in two different temperature bodies, when approached together, it starts to develop a current in a closed loop. So just like we had seen here in this example, in this figure, so what will happen here is we have a hot junction or a hot point, and we have a cold junction or a cold point, and here we put our thermocouple. So this thermocouple will do nothing but it will measure the I flowing through this. So this is the experimental setup for a thermocouple. And again, with the rise in the temperature, the current would rise. So it would have a positive coefficient. Now it is important here to see a factor that in all the three classes of the temperature sensors that we studied here, we studied about the thermistors, we studied about the RTDs, and we saw the thermocouples. And invariably in all the three, what we are doing is we are bringing in contact a measuring end to a hot body. So let us say what is happening here is I have a plate whose temperature, let's say it is on flame, and we bring in contact all the three, be it a thermistor, be it a RTD, or be it a thermocouple. Now if you can see, all depends on this contact. So these three classes of temperature resistance or temperature sensors are called as contact type temperature sensors. So what we are doing invariably here is we are bringing in contact our sensor with a hot body. Now there is always a limit to physical contacts. How? Let us say this flame is 200 degrees Celsius or 300 degrees Celsius. In that condition, it is possible for us to think of designing a system that can come in contact and measure these values. But say our temperature goes on to become 2000 degrees Celsius. Now, this 2000 degrees Celsius will cause secondary effects such as ionization. So the gas or the air there will start to ionize, and the surrounding areas will become so highly warm, in temperature that it would be practically impossible for us to go near to that surface, leave apart, putting our sensor onto contact, because it will create a burnout. So for very high temperatures, say above 1000 degrees Celsius, we have to use non-contact type temperature sensors. Pyrometry is one technique. We will not take up this in this class. We will start with this in the next section. But pyrometry is one of these class wherein we do not bring in the sensor in contact with our surfaces, but without touching, we analyze the temperature. Okay, so we will end the discussion on temperature sensors here. We'll take a short break and then we will start with pressure measurements. Okay, so let us now move on to the second topic after temperature measurements. Let us now start. Pressure transducers. Now, one thing that we have understood from designing temperature transducers, that we have to eventually do some sort of energy conversion. That is the basic need of a transducer. That is the basic function of a transducer. And there is a unknown to be measured, and this unknown, when applied to uh, an entity with known parameters, would cause changes in accordance with the quantity of unknown. Now, what I'm trying to say here is, when you design any transducers based system and you have to do any kind of measurement, be it temperature measurement, be it pressure measurement, be it volume measurement, whatever it is, there is this closed box with known values, and there is this input that is unknown. Now, when this input that is unknown is applied, it causes changes, and these amount of change is attributed to the input being applied. Like we saw in the previous cases, that with the application of temperature, the resistance was changing and we were actually measuring the resistance. The changes in the resistance were comprehending to the changes in the temperatures. Similarly, when we study pressure transducers, there is a class of transducers that is called as resistance based pressure transducer. Now suppose if we take that example again and we say that we have a conducting material and it has a resistance R,